Hi, this is Lucas from Yoast Quantum, and today we are showcasing a demo of the HHL algorithm, which is a quantum algorithm used for solving systems of linear equations, ideally ones that are large and sparse, with potentially exponential speedup over classical methods. This came up in a project we did with Deutsche Bundesbank, where we investigated whether quantum computing can support their macroeconomic simulations. And here we partnered with hardware provider AQT, who gave us access to their ion trap machines to do this proof of concept. The machine that we are using is called IBEX Q1, and you can also access it using their cloud service Arnica. Let's start the demo. So on the left, you see a Jupyter notebook. In principle, it's very easy to connect to the AQT machines. You just need to import this package, Qiskit AQT provider. And from that, with your access token, load the provider and the sampler that you want to use. And then you're good to go. So in the beginning, we are just importing some things. And then we can encode our first example. So this is, of course, a very small example. And it's also very specific to this task because it is easy to encode for reasons that are too complicated to explain now. But here is how you do it. So this is what the code for a quantum computer looks like with Qiskit. And in a minute, you will see the result. So this is what we call a quantum circuit. This is a bit of a high-level representation, though, because we still need to map that to the architecture of the AQT machine so that it can actually be run. And this is what it looks like after this mapping. So it does the same thing, just looks a bit different. And then we need to send that to the machine. So this is very simple. You just need to run the sampler with that circuit, and then we will get a result. But here, let me give you an exclusive look into the AQT system. So what you can see here is an interface that they have where on the top, you just see the jobs that are being sent to the machine. On the bottom left, you see a picture of the ions that they hold in place to facilitate quantum computing. And on the bottom right, that's the important part, you see histograms that reflect something about the state of those ions. And just now on the top, you saw the job that I sent coming in, and it's getting loaded, the machines are getting calibrated, and then eventually it will, the calculation will happen and the states will change radically. So any second now. Yes, so now you see the histograms look completely different from, of the first four ions look completely different from the rest because our algorithm here used only 4 qubits. So the others are unaffected, and yeah, something certainly changed. And then what exactly the results are, we can see in the notebook when we download the results from the AQT system again. And this is what it looks like. So it's this type of histogram where the purple bars, they correspond to the result that we just got from the hardware. And then the blue ones is a simulation that we did here, which assumes that there is no noise. And just so we have something to compare the hardware result to. And as you can see, at least in the overall shape, the hardware result is quite similar to the shape of the simulation. So this means that the algorithm actually works and does something. But yeah, what does this mean? Because this is some sort of histogram, but we wanted to solve this matrix equation. And it's somewhat complicated, but in a nutshell, the result is encoded into the bins 1 and 3 here. So the result of this equation is, of course, a vector with 2 entries, and these are encoded into the bins 1 and 3. The bins 0 and 2 are sort of like a trash that gets accumulated during the algorithm. So this is a feature of the algorithm. This is not something that is an error of the machine or something. And the you can get the exact result out of this, but for now I just want to make the point that the relation between these two is supposed to be about 1/9. You can see in the simulation this is pretty much exactly the case, and in the hardware we are of course relatively close to it, although not exactly there. And then we wanted to go beyond this extremely specific example and implement something else that is more variable. You can also implement HHL for just any matrix, but then it's not really efficient and you will not get good results. So here what we did is we implemented it for diagonal matrices that get specifically powers of 2 on the diagonal, but then at least you can make some changes, where in this first specific example we couldn't make any changes. So now we can play around a bit. And so let's just see how this minimal first case works out, where the numbers on the diagonal are only 1 and 2, and it's still a 2 by 2 matrix, and this is what that looks like. Again, the result is encoded in bins 1 and 3, so not too bad either. And then we can increase a parameter of the algorithm, which is called the precision. This allows us to encode more numbers. So first we try if we can still produce the same result with the previous for the previous matrix with more precision. And you can see in the on the machine that around this time, this when this happens, because now we invest 1 more qubit for precision, we now affect the first 5 qubits. So this is what the result looks like. So for the small matrix, it's for the matrix of only 1, 2, it's the same as before. And then we can also now encode the number 4. And then if we do HHL on this matrix 2, 4, we get this kind of result, which looks a bit different because the result is still encoded in bins 1 and 3, but now we have a lot more results or a lot more shots going into these trash bins 0 and 2. And this is just because we allow, we don't use the full range of encoding that we can do. We can encode 1 to 4, but we chose here to use a matrix that uses only high numbers, 2 and 4. And therefore, a lot of stuff gets put in this trash. And this is just how the algorithm is. And it does tell you, it is also relevant for getting out the exact result in the end. In any case, in the last example, we want to show what you really want to do, of course, with the HHL algorithm, which is scaling up dimension. Eventually, you would want to run this thing for matrices with thousands of dimensions, and maybe not only diagonal matrices, but still sparse that you have to ensure. So here we are just going up a bit in dimension to 4, and then we see what we get. And I want to point out that this algorithm is extremely demanding. So it doesn't use that many qubits, but it needs to perform a lot of operations on those qubits. And therefore it's very susceptible to noise. And of course, hardware exists, and it's great that we get results that prove that the algorithm works. But this one in particular is really demanding, and we will see that already at this size of matrix, it is quite difficult to get usable results. So this is what we get. It's now the solution bins are 1, 3, 5, and 7, so all the uneven numbers. And as you can see, there's quite large differences also in terms of overall shape between the blue and the purple bars in those bins. And it's probably fair to say that on the hardware, the hardware results still have some structure that is probably influenced by the problem, but this is now too far, of course, to be used in a calculation. But we are getting there. Like the smaller examples worked. This example is not fully random, at least. And whenever we scale up, we can then solve huge matrix equations that are relevant for macroeconomic simulations. And with that, we want to thank again our partners, AQT and Deutsche Bundesbank, for their cooperation, and we hope that you learned something new today.